Tonight, we're going to talk about the crisis unfolding in cosmology right now. For decades, we thought we understood the scale of our universe. We had measurements, calculations, models that told us how big everything was, how far galaxies stretched, how much time the universe needed to build the structures we see today. And then Webb looked deeper than any telescope before it. What it saw wasn't just unexpected. It was impossible. Galaxies that shouldn't exist, appearing in places they had no right to be. Structures forming billions of years too early. A universe that wasn't just bigger than we thought, but fundamentally different from what our best theories predicted. And by the end of tonight, you're going to understand why everything we thought we knew about the true scale of the universe was built on incomplete data, and how Webb's discoveries are forcing us to rewrite the cosmic story from the very beginning. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. For decades, we had it all figured out. The universe was 13.8 billion years old, born in the Big Bang. After that initial explosion, space expanded and cooled. About 380,000 years later, the universe became transparent. Light could finally travel freely through space. But stars didn't form immediately. There was a period astronomers call the Cosmic Dark Ages, lasting from about 380,000 years to about 100 to 200 million years after the Big Bang. During this time, the universe was dark, filled with hydrogen and helium gas, but no stars to light it up. Eventually, gravity pulled that gas together. The first stars ignited around 100 to 200 million years after the Big Bang. These population 3 stars, as we call them, were massive, pure hydrogen and helium with no heavier elements. They burned hot and died fast, living only a few million years before exploding as supernovae. Those explosions scattered the first heavy elements across space: carbon, oxygen, iron, and these elements would be incorporated into the next generation of stars. This process took time, lots of time. Our models predicted that the first small galaxies wouldn't form until about 300 to 500 million years after the Big Bang. And these early galaxies would be primitive. Small collections of stars, maybe a few million to a few tens of millions, irregular in shape, without organized structure. No spiral arms, no clear centers, just chaotic clumps of stars held together by gravity. Over the next few billion years, these small galaxies would merge. 2 small galaxies colliding would form a slightly larger one. That larger galaxy would collide with others, growing bigger each time. It was cosmic construction, building cathedrals from individual bricks over billions of years. By the time the universe was about 1 billion years old, we expected to see galaxies containing maybe 100 million to a few hundred million stars. Still relatively small, still irregular, but starting to show hints of structure. By 2 billion years, galaxies might reach 1 billion stars. By 3 billion years, organized structures like spiral arms might begin to form. The Milky Way, our home galaxy with its 400 billion stars and its beautiful spiral structure, took about 13 billion years to form. That timeline made sense. It matched what we knew about gravity, about how gas collapses to form stars, about how galaxies merge and grow. The math worked. The physics worked. Hubble Space Telescope observations seemed to confirm this timeline. When Hubble looked at galaxies about 10 billion light-years away, Seeing them as they were 10 billion years ago, those galaxies looked more primitive than nearby ones. When Hubble pushed to its limits, imaging galaxies about 12 to 13 billion light-years away, seeing them as they were just a few 100 million years after the Big Bang, those galaxies were small and faint, exactly as predicted. We also knew how many galaxies should exist at different distances. Close to us, in the recent universe, galaxies are common. Space is full of them. But as you look farther back in time, galaxy density should decrease. Fewer galaxies exist in the young universe because they haven't had time to form yet. Our calculations suggested that when the universe was 500 million years old, there might be 10 to 20% as many galaxies per unit volume as exist today. When the universe was 300 million years old, maybe only 1 to 5% of today's density. This made sense because galaxies form gradually. You start with very few, and the number increases over time as more gas collapses and more structures form. We estimated the observable universe contained about 200 billion to 2 trillion galaxies total. That's already an incomprehensible number. But it was a number we trusted, based on decades of observations and solid theoretical foundations. The observable universe itself was calculated to be about 93 billion light-years in diameter. That's not the same as the age of the universe times 2. The universe is 13.8 billion years old, so you might think light could only have traveled 13.8 billion light-years. But space has been expanding all this time. Objects that emitted light 13.8 billion years ago are now much farther away because space itself stretched while the light was traveling. When we account for that expansion, the most distant objects we can see are now about 46.5 billion light-years away. Double that, and you get the 93 billion light-year diameter. Everything we could observe fit inside that sphere, and within that sphere, structure was organized in a specific way. At the smallest scales, you have individual galaxies. Galaxies group together into galaxy clusters containing dozens to thousands of galaxies. Clusters group into superclusters containing tens of thousands of galaxies. And superclusters form part of the cosmic web, a structure of filaments and voids that spans the entire observable universe. This web took billions of years to form. Gravity pulled matter together along filaments, creating the threads of the web. Between the filaments are vast voids, regions nearly empty of galaxies. Our models predicted this structure started forming when the universe was at least a few 100 million years old, with the cosmic web taking billions of years to become as defined as what we see today. Everything fit together. The timeline, the structure, the galaxy counts, the evolution from simple to complex. We had a complete picture of cosmic history from the Big Bang to today. It was elegant. It was testable. It was confirmed by multiple independent observations. We called this the Lambda Cold Dark Matter Model, or Lambda CDM for short. Lambda represents dark energy, the mysterious force causing the universe's expansion to accelerate. Cold dark matter represents the invisible matter that makes up most of the universe's mass, providing the gravitational scaffolding for galaxies to form. This model had been refined over decades. It matched the cosmic microwave background, the afterglow of the Big Bang. It matched the large-scale structure we observe. It matched the expansion rate measurements. It matched galaxy evolution as Hubble observed it. There were a few minor puzzles, things that didn't quite fit perfectly. The Hubble tension, where different methods of measuring the expansion rate gave slightly different answers. Some observations suggesting galaxies might have slightly more organized structure than expected at certain epochs, but these were seen as measurement uncertainties, small discrepancies that would be resolved with better data. Nobody expected the model to be fundamentally wrong. Nobody expected James Webb to reveal that almost everything about our timeline was off. Then, the James Webb Space Telescope launched on December 25, 2021. The telescope was designed to see what Hubble couldn't. While Hubble observed primarily in visible light, Webb observes in infrared. This difference is crucial for studying the early universe. Light from the most distant objects is redshifted, stretched to longer wavelengths by cosmic expansion. Light that starts as visible or ultraviolet gets stretched into infrared by the time it reaches us. The farther away something is, the more its light is redshifted. Webb's infrared vision allows it to see objects so distant that their light has been stretched completely out of visible wavelengths. Objects Hubble could barely detect or couldn't see at all. Webb also has a much larger mirror than Hubble. Webb's mirror is 21.3 feet across, with a collecting area about 6.25 times larger than Hubble's. More mirror means more light collected, which means fainter objects become visible. Combined with its infrared capability, Webb can see galaxies forming in the first few 100 million years after the Big Bang, with unprecedented clarity. This is what it was built for. To look at the universe's first light, to see how the first galaxies formed, to test our models of cosmic dawn. On July 12, 2022, the first deep field image from Webb was released. The target was a galaxy cluster called SMACS 0723. The image showed the cluster in stunning detail, but even more impressive was what lay beyond it. Thousands of distant galaxies, stretching across cosmic time, each one appearing as a small smudge or arc of light. Astronomers immediately began analyzing these galaxies, measuring their distances through spectroscopy, determining their properties, comparing them to predictions. And almost immediately, something was wrong. The galaxies in the deepest background, the ones that should be the most primitive, weren't primitive at all. They had structure. They had mass. They looked organized. One of the first anomalies identified was a galaxy designated Galaxies Z13. Spectroscopic analysis confirmed it existed just 300 million years after the Big Bang. That was already pushing the boundaries of what models predicted, but possible within the Lambda CDM framework. But this galaxy contained approximately 1 billion stars. 1 billion. At 300 million years after the Big Bang. For context, forming 1 billion stars requires an enormous amount of gas to collapse, fragment, and ignite. Even under ideal conditions, with perfectly efficient star formation, this should take at least 500 million to 1 billion years. Galaxies Z13 did it in 300 million. The timeline didn't work. Then came Sears 933, another early galaxy from Webb's Cosmic Evolution Early Release Science Survey. This galaxy also existed around 300 million years after the Big Bang. It was massive, containing hundreds of millions of stars, and showed signs of organized structure. Not a chaotic clump, but something with shape, with internal organization. Then JWST 13-0, discovered as part of the JWST Advanced Deep Extragalactic Survey. This galaxy existed about 330 million years after the Big Bang. Again, massive. Again, organized. Again, containing far more stars than should be possible in that time frame. These weren't outliers. They were everywhere Webb looked. The JWST survey alone found dozens of galaxies in the first 500 million years of cosmic history that were too massive, too structured, too mature for their age. But the real shock came with JWST GSZ 14-0. Initial analysis suggested this galaxy existed just 290 million years after the Big Bang, less than 300 million years. And it contained something that absolutely shouldn't exist at that point in cosmic history: a supermassive black hole. The black hole at this galaxy's center had a mass estimated at several million times the mass of our Sun. Black holes, that massive, shouldn't exist in the early universe. Here's why. Black holes form when massive stars die and collapse. But a stellar mass black hole, formed from a single star, might be 10 to 100 times the mass of the Sun. To grow from stellar mass to supermassive, millions or billions of solar masses, the black hole needs to feed. It needs to accrete matter from its surroundings. But there's a limit to how fast a black hole can grow. As matter falls toward a black hole, it heats up and emits radiation. That radiation creates pressure that pushes against infalling matter. This is called the Eddington limit, and it sets a maximum rate at which a black hole can accrete mass. Even feeding at the Eddington limit constantly, it takes at least hundreds of millions of years to grow a black hole from stellar mass to millions of solar masses. JWST GSZ 14-0 had less than 300 million years. And that assumes the black hole formed immediately at the start of that period, which it couldn't have, because you need stars to form first, live their lives, and then collapse. The timeline was impossible. Unless something about our understanding of black hole growth was wrong. Unless black holes in the early universe could somehow bypass the Eddington limit and grow much faster than physics should allow. Or unless these black holes didn't form from collapsing stars at all, but through some exotic process we don't understand. Either way, the observations didn't match the theory. As Webb continued observing, the problem only got worse. The density of galaxies in the early universe was far higher than predicted. When the Lambda CDM model predicted the universe at 500 million years old should contain maybe 10 to 20% of today's galaxy density, Webb found something closer to 50 to 70%. 3 to 5 times more galaxies than expected. At 300 million years, where models predicted 1 to 5% of today's density, Webb found 20 to 30%. 5 to 10 times more galaxies than expected. These aren't small discrepancies. These are fundamental mismatches between theory and observation. And it wasn't just the number of galaxies. It was their mass distribution. Surveys found that massive galaxies, ones containing 10 billion stars or more, were surprisingly common in the early universe. According to pre-Webb models, galaxies that massive shouldn't exist until the universe is at least 1 to 2 billion years old. Yet Webb found them at 500 million years. At 700 million years. Massive galaxies that had no business existing yet. One study analyzing Webb data found galaxies in the early universe that were as massive as the Milky Way. Our galaxy took 13 billion years to accumulate its 400 billion stars. Webb was seeing Milky Way mass galaxies when the universe was less than 1 billion years old. How do you compress 13 billion years of growth into less than 1 billion? The math doesn't work. Even if star formation was perfectly efficient, Even if every bit of available gas turned into stars with no waste, you can't form that many stars that fast. Gas clouds can only collapse so quickly. Stars can only form so fast. There are physical limits built into the process. Gravity works at a certain speed. Gas has pressure that resists collapse. Forming stars requires cooling, and cooling takes time. You can't speed it up indefinitely. Yet somehow, the early universe was doing exactly that, forming massive galaxies orders of magnitude faster than our models predicted. The structure of these early galaxies was equally surprising. Pre-Webb models predicted that early galaxies would be irregular, chaotic, without organized structure. Spiral arms and galactic disks should take billions of years to form. But Webb found galaxies with disk-like structures at 700 million years. Galaxies with elongated shapes, suggesting rotation and angular momentum at 500 million years. Galaxies showing signs of spiral arms at 1 billion years, billions of years earlier than expected. The universe was organized from almost the very beginning, not chaotic and primitive, but structured and sophisticated. Another shocking discovery was the presence of protoclusters in the early universe. Protoclusters are the ancestors of today's massive galaxy clusters. They're regions where dozens of galaxies are forming close together, bound by gravity, destined to merge into a single enormous cluster over cosmic time. Our models predicted protoclusters wouldn't form until the universe was at least 500 million to 1 billion years old. Webb found them at 300 to 400 million years. Not just a few galaxies near each other by chance, but gravitationally bound structures already showing the organization that will define the cosmic web. This meant large-scale structure was forming far earlier than our models allowed. The cosmic web, that vast network of filaments and voids, wasn't something that gradually emerged over billions of years. Its foundations were being laid in the first few 100 million years. Chemical composition added another layer of confusion. When the universe began, it contained only hydrogen and helium. Everything heavier, what astronomers call metals, had to be created in stars through nuclear fusion. The first generation of stars. Population. 3 stars were pure hydrogen and helium. When they died, they enriched the surrounding gas with heavier elements. The second generation incorporated those elements. The third generation incorporated even more. This enrichment process takes time. You need multiple generations of stars living and dying to build up significant metal content. Our models predicted that galaxies in the first few 100 million years would be metal poor, containing mostly hydrogen and helium, with only traces of heavier elements. But Webb's spectroscopy showed surprisingly high metal abundances in some early galaxies. Metal content that should require multiple stellar generations to produce, present when the universe was barely old enough for 1 or 2 generations. This suggested the cycle of star formation, and death was happening incredibly fast in the early universe. Stars forming, living their brief lives, exploding, enriching the gas, and that gas forming new stars, all in time frames measured in tens of millions of years rather than hundreds of millions. The pace of chemical evolution was far faster than our models predicted. By late 2022 and into 2023, as more Webb data accumulated, astronomers began using the term crisis in cosmology. This wasn't hyperbole. The Lambda CDM model, our standard model of cosmology, refined over decades and tested against countless observations, was failing to explain Webb's observations, not failing in minor ways. Failing fundamentally. The model predicted a certain timeline for galaxy formation. Webb showed that timeline was wrong by factors of 2 to 5. The model predicted certain galaxy densities at different epochs. Webb showed densities 3 to 10 times higher. The model predicted primitive, irregular galaxies in the early universe. Webb showed organized, massive, structured galaxies. Every major prediction about the early universe was wrong. Some astronomers initially questioned whether the observations themselves might be wrong. Maybe the redshift measurements were incorrect. Maybe these galaxies weren't as distant as they appeared. But Webb's spectroscopy is extremely precise. Redshift measurements are based on identifying specific spectral lines from elements like hydrogen and oxygen, and measuring how much those lines have been shifted to longer wavelengths. It's one of the most reliable measurements in astronomy. Multiple independent teams analyze the data and confirm the redshifts. The galaxies really were that distant. They really were forming when the universe was only a few 100 million years old. Others suggested maybe star formation in the early universe was just more efficient than we thought. Maybe conditions back then allowed gas to convert into stars at higher rates. But even pushing efficiency to theoretical maximums, where every available bit of gas becomes a star with zero waste, the numbers barely improve. You still can't form billion-star galaxies in 300 million years. The timeline is too short. Some researchers proposed that maybe the first stars were more massive than we assumed. If population 3 stars were typically 100 to 300 times the mass of the Sun, as some models suggest, they would live very fast, die very fast, and enrich the cosmos with heavy elements much more quickly than normal stars. This could speed up chemical evolution. But it doesn't solve the mass problem. Even if enrichment happens faster, you still need time for gas to collapse into stars. Multiple rounds of collapse and formation take time, no matter how massive individual stars are. The Hubble tension, already a puzzle before Webb, became worse. The Hubble tension refers to a discrepancy in measurements of the universe's expansion rate, called the Hubble constant. When you measure the Hubble constant using the cosmic microwave background, the afterglow of the Big Bang, you get a value around 42 miles per second per megaparsec. When you measure it, using observations of nearby galaxies and supernovae, you get around 45 miles per second per megaparsec. These numbers disagree by about 9%, far more than measurement uncertainties can explain. Before Webb, astronomers hoped better observations might resolve this tension by refining one measurement or the other. Instead, Webb's precise distance measurements of faraway galaxies have confirmed that the tension is real. The expansion rate seems to be different depending on where and when you measure it. If the expansion rate isn't constant, if it varied over cosmic history in ways our models don't account for, then all our calculations of distances and ages become uncertain. Maybe the universe is older than 13.8 billion years. Maybe it expanded faster in early epochs. If the universe is older, that gives more time for structure to form, potentially explaining some of Webb's early galaxy observations. But changing the age creates other problems. The cosmic microwave background gives us a very precise age based on well-understood physics. To change that age, you have to change the physics, which affects everything else we think we know about the universe. Dark matter distribution also became problematic. Webb's gravitational lensing observations, where massive objects bend light from more distant sources, allow us to map how dark matter is distributed. These maps show dark matter clumped in ways that don't quite match simulations. In some regions, it's more concentrated than predicted. In others, it's more spread out. The discrepancies aren't huge, but they're consistent. Something about how dark matter behaves, or how it clumps together over time, doesn't match our models. If dark matter clumps faster, that could help explain rapid galaxy formation. Denser dark matter halos provide stronger gravitational wells, pulling in normal matter more quickly. But this would require dark matter to interact with itself, or with normal matter, in ways we haven't detected. It would require new physics. Some cosmologists proposed modifications to the Lambda CDM model. Maybe dark energy, the mysterious force accelerating cosmic expansion, was stronger in the early universe. That could affect how structure forms. Maybe dark matter has properties we don't understand, like weak self-interactions that change its distribution. Maybe the initial conditions right after the Big Bang were different from what the cosmic microwave background suggests. Tiny variations in those initial conditions could cascade into large differences in structure formation, but every proposed modification created new problems. Change one parameter to fix early galaxy masses, and you break the fit to large-scale structure observations. Adjust another parameter to match galaxy densities, and you mess up predictions for the cosmic microwave background. The model is interconnected. Change one piece, and everything shifts. Finding a modification that explains Webb's observations without breaking everything else has proven extremely difficult. Some researchers began exploring more radical ideas. What if our understanding of gravity is wrong on cosmic scales? What if general relativity, Einstein's theory that's passed every test for over a century, breaks down in the extreme conditions of the early universe? Modified gravity theories have been proposed before, mostly to explain dark matter without invoking invisible particles. These theories suggest that gravity behaves differently at very large distances or very low accelerations. If gravity was stronger in the early universe, that could help structure form faster. But modified gravity theories have their own problems, and most have been ruled out by observations. The few that remain are highly speculative and would require overthrowing one of the most successful theories in all of physics. Other researchers looked at exotic possibilities. What if there was a period of rapid structure formation triggered by some unknown process in the early universe? What if primordial black holes formed in the Big Bang rather than from collapsing stars, seeded early galaxies? What if dark matter decayed or interacted in the early universe in ways it doesn't now, temporarily boosting structure formation? These ideas are speculative, hard to test, and would require physics beyond our current understanding. But the observations demand explanation. You can't just ignore data that contradicts your model. Science advances by updating theories when new observations don't fit. That's what's happening now. Cosmology is in a period of upheaval, trying to reconcile decades of solid theory with observations that don't match. It's uncomfortable for many astronomers who've spent careers working within the Lambda CDM framework. But it's also exciting, because when your theories fail to match reality, it means there's something new to discover. Some fundamental aspect of how the universe works that we haven't understood yet. So what does all this mean for the true scale of the universe? If Webb's observations are forcing us to rethink galaxy formation timelines, they're also forcing us to rethink how much structure exists in the cosmos. The observable universe is still 93 billion light-years across. That measurement hasn't changed. It's based on the age of the universe and the speed of light. both of which are well established. But what fills that volume is radically different from what we calculated. Before Webb, we estimated 200 billion to 2 trillion galaxies in the observable universe. Those estimates were based on galaxy surveys covering small patches of sky, then extrapolating to the full volume. The extrapolations assumed galaxy density decreased as you looked back in time. Fewer galaxies in the young universe, more in the mature universe. But Webb shows that assumption was wrong. Galaxy density in the early universe is much higher than predicted. If we recalculate based on Webb's observations, the total number of galaxies could be significantly higher. Some estimates now push toward 5 to 10 trillion galaxies. That's not just a revision. That's a fundamental recalculation of how much organized structure exists in the cosmos. Each galaxy contains billions to trillions of stars. Each star potentially hosts planets. The sheer amount of matter organized into structures is staggeringly larger than we thought. But it's not just quantity. It's the nature of that structure. We thought the early universe was simple and gradually became complex. We thought structure emerged, slowly, over billions of years. Webb is showing the universe was complex from almost the beginning. Organized structure appeared in the first few 100 million years. The cosmic web started forming immediately. Massive galaxies assembled in timeframes we thought impossible. This changes our understanding of how the universe works at the most fundamental level. It suggests the processes that create structure are far more powerful, far more efficient than we understood. Gravity works faster. Gas collapses quicker. Stars form more readily. The universe has a natural tendency toward organization that's stronger than our models predicted. And if the observable universe is more densely packed with structure, what about the universe beyond what we can see? The observable universe is limited by the speed of light and the age of the universe. Beyond that horizon, there's more universe. We can't see it directly, but we can infer its existence. Most cosmological models suggest the total universe is much larger than the observable portion. Some estimates say it's at least 250 times larger in radius. Others suggest it could be exponentially larger if cosmic inflation, the rapid expansion in the first fraction of a second after the Big Bang, extended the universe beyond what we calculated. If the universe beyond our horizon follows the same patterns Webb is revealing, if it's populated with the same density of galaxies, forming at the same accelerated pace, then the total amount of structure in reality is almost incomprehensibly larger than we thought. Take the observable universe's trillion-plus galaxies and multiply by whatever factor the total universe is larger. 250 times larger in radius means about 15 million times larger in volume. 15 million times a trillion galaxies. The numbers stop making sense at that scale. But the implication is clear. What we can see is a tiny sample, and that sample is richer, denser, more complex than we calculated. The total scale of structure in the universe is correspondingly larger. There's also a temporal dimension to scale that Webb illuminates. If galaxies formed billions of years earlier than we thought, the period of active structure formation in the universe is longer. The window during which planets could form, during which life could emerge, during which civilizations might arise, extends farther back in cosmic history. This has profound implications for questions about life beyond Earth. If habitable planets could form when the universe was 1 billion years old, instead of several billion years old, That's several billion additional years for life to emerge and evolve. If intelligent civilizations can arise earlier, they've had more time to develop technology, to spread across their galaxies, to leave detectable signatures. The Fermi paradox, the puzzle of why we see no evidence of extraterrestrial civilizations, becomes even more puzzling when we realize the universe has been capable of hosting them for longer than we thought. Maybe life is incredibly rare despite all those opportunities. Maybe intelligence is even rarer. Maybe civilizations inevitably destroy themselves before reaching the point where they're detectable across interstellar distances. Or maybe we're looking in the wrong places, at the wrong times, for the wrong signals. Webb doesn't directly search for life, but its revelations about the universe's capacity to support life are profound. The scale of possible homes for life is larger than we calculated. The timeline for life's emergence is longer than we thought. The cosmic real estate available for biology is more abundant at earlier epochs. All of this expands the scale of life's potential presence in the universe. Another aspect of scale involves the distribution of matter. Before Webb, we thought matter was distributed roughly evenly on large scales, with clumps that grew gradually over time. Webb shows matter was clumping faster and earlier. The cosmic web formed sooner. Galaxy clusters assembled quicker. Superclusters emerged earlier. This means the universe's large-scale structure, that network of filaments and voids spanning hundreds of millions of light-years, was taking shape in the first billion years. We thought it took 5 to 10 billion years. The pace of organization on the largest scales is far faster than predicted. And if large-scale structure forms faster, that affects everything from gravitational wave backgrounds to the distribution of dark matter to the evolution of individual galaxies within that structure. It's all connected. Change one thing, and everything else adjusts. The true scale isn't just about size or quantity. It's about recognizing that our understanding was built on incomplete observations. Hubble could see far, but not far enough. Hubble could detect galaxies in the early universe, but only the brightest ones. Fainter galaxies, smaller galaxies, more distant galaxies were invisible. We extrapolated from what Hubble could see, assuming we understood the full population. But we were seeing only the tip of the iceberg. Webb, with its larger mirror and infrared capability, is seeing the rest of the iceberg. And it's much larger than we thought. The analogy isn't perfect, because icebergs are mostly below the waterline, while we're seeing galaxies across time. But the principle holds. We were working with incomplete data and making assumptions to fill the gaps. Those assumptions turned out to be wrong. The true scale is revealed, not just by measuring farther, but by measuring better. Higher resolution, better sensitivity, broader wavelength coverage. All of these reveal details we missed before, and those details matter. They change the story. Let's think about what the scale of structure in the early universe tells us about the Big Bang itself. The Big Bang wasn't an explosion in space. It was an expansion of space. All of space, all at once, growing from an infinitely hot, infinitely dense state. In the first fraction of a second, the universe underwent inflation, expanding exponentially fast. When inflation ended, the universe was filled with energy that began converting into matter and radiation. This is called reheating, and it set the initial conditions for everything that followed. The cosmic microwave background, the afterglow we observe today, shows tiny temperature fluctuations across the sky. These fluctuations represent density variations in the early universe. Regions that were slightly denser than average would grow into galaxies and clusters through gravitational attraction. Our models take those density fluctuations and simulate how they should evolve over time. The simulations match observations of the universe's large-scale structure pretty well, but they don't match Webb's observations of the early universe. The structures Webb sees are too mature, too massive for the density fluctuations we observe in the cosmic microwave background to have produced. It's like the seeds were too small to grow the trees we're seeing. This suggests something is wrong, either with our understanding of initial conditions or with how structure grows from those conditions. Maybe the density fluctuations were larger in certain regions than the cosmic microwave background suggests. Maybe there were additional seeds for structure formation that we haven't accounted for. Maybe the physics of structure growth is different in the early universe, with processes we don't understand boosting efficiency. Any of these possibilities would require revising our understanding of the Big Bang and its immediate aftermath. And that would change our understanding of the universe's total scale, because initial conditions determine how structure evolves over cosmic history. There's also the question of what lies beyond the cosmic horizon. The observable universe has an edge, not a physical boundary, but an information boundary. Light from regions beyond that edge hasn't had time to reach us yet. As time passes, light from farther regions will arrive, and our observable universe will grow. But the universe itself is expanding, and that expansion is accelerating. This means some regions are receding from us, faster than light can travel. We'll never be able to see them, no matter how long we wait. The light from those regions will never reach us, because space between us and them is stretching faster than light can cross it. This creates a fundamental limit to how much of the universe we can ever observe. And it means there's structure beyond our reach, galaxies we'll never see, cosmic history we can never directly access. But if the region we can see is more densely populated, more rapidly evolved, more structured than we thought, it's reasonable to assume the region beyond our horizon is similar. The cosmological principle, the idea that the universe is roughly the same everywhere, suggests that what we observe is representative. If our patch is full of galaxies, the rest of the universe is probably full of galaxies too. But full now means something different than it did before Webb. It means more galaxies, forming earlier, evolving faster, organized sooner. The scale of structure beyond our horizon, in the parts of the universe we can never observe, is correspondingly larger. This is where scale becomes philosophical. We're talking about regions of space we can never see, galaxies whose light will never reach us, structures that exist but are forever beyond our knowledge. The true scale of the universe includes all of that. Not just what we can measure, but what we can infer must exist based on the principles of physics and cosmology. And Webb's observations are changing those inferences. We're inferring more structure, more complexity, more organization than our pre-Webb models suggested. The universe as a whole, not just the observable part, is richer than we thought. Webb's discoveries also reveal something about the limits of our knowledge. For centuries, we've been expanding our understanding of cosmic scale. Copernicus showed Earth wasn't the center of the solar system. Galileo showed the Milky Way was made of countless stars. Hubble showed the Milky Way was one galaxy among billions. Each revelation expanded our sense of scale, and each came with the hope that we were approaching a final understanding. Webb is showing we're not even close. Our models were wrong about galaxy formation timelines, wrong about galaxy densities, wrong about structure, evolution, wrong about how quickly the universe organized itself. If we were this wrong about the early universe, What else are we wrong about? How many assumptions do we make that seem reasonable but turn out to be false when better data arrives? How much of our understanding is built on extrapolations that don't hold up under scrutiny? These questions don't undermine the scientific method. They're part of it. Science is about building models, testing them against observations, and revising them when they fail. That's what's happening now. Webb is providing observations that don't match our models, and we're revising our understanding. But it's humbling. We thought we had cosmic evolution figured out. We thought we understood the timeline from the Big Bang to today. We were confident enough in that understanding to build detailed models to make precise predictions. And we were wrong, not slightly wrong, fundamentally wrong. The universe evolved differently than we predicted, faster and more efficiently. If our models can be that wrong about something as fundamental as galaxy formation, what does that say about the limits of our knowledge? Maybe we're still in the early stages of understanding the cosmos. Maybe, in a century, astronomers will look back at our current theories the way we look back at pre-Copernican astronomy. Well-intentioned, based on the best available evidence, but ultimately missing crucial pieces of the picture. That's not a reason for despair. It's a reason for humility. We should hold our theories provisionally, always ready to revise when new data arrives. We should recognize that what we know is dwarfed by what we don't know. And we should keep observing, keep questioning, keep pushing the boundaries of knowledge. The true scale of the universe isn't just measured in light years or galaxy counts. It's measured in how much remains unknown. And by that measure, the scale is vast. Webb will continue operating for at least another 10 to 15 years, possibly longer if its systems remain healthy. Every observation it makes will add to our understanding, and every addition will likely deepen the mysteries rather than resolve them. That's been the pattern so far. Each new dataset from Webb has raised more questions than it answered. Each discovery has made the universe stranger, more complex, more challenging to our theories. Future telescopes will push even deeper. NASA and other space agencies are already planning next-generation observatories. Telescopes with even larger mirrors, even better sensitivity, even broader wavelength coverage. Ground-based observatories are also improving. The extremely large telescope, currently under construction in Chile, will have a mirror over 128 feet across. It will be able to study individual stars in galaxies billions of light-years away, resolving details Webb can only glimpse. Radio telescopes are also advancing. The Square Kilometre Array, an international project, will be the most sensitive radio telescope ever built, capable of detecting signals from the early universe that optical telescopes miss. Gravitational wave observatories are improving too. As they become more sensitive, they'll detect collisions of black holes and neutron stars from earlier epochs, giving us another window into the early universe's structure. Each of these future instruments will reveal new aspects of cosmic scale. Each will test our theories, and if history is any guide, each will find discrepancies that force us to revise our understanding. That's how science works. It's an iterative process of observation, theory, revision, and refinement. We're never done. There's always more to learn. But that's also what makes it exciting. The universe is not a puzzle with a fixed number of pieces that we're slowly assembling. It's a puzzle that reveals new pieces every time we think we're close to finishing. And those new pieces change the picture, making it richer and more interesting. Webb is showing us a universe that's bigger, not just in physical dimensions, but in complexity, in the density of structure, in the pace of evolution, in the efficiency of organization. The true scale is larger than we thought because the universe is more capable than we predicted, more capable of forming structure quickly, more capable of organizing complexity early, more capable of creating conditions for diversity and evolution. And if the universe is more capable, that changes everything about how we think about our place within it. We're not observers of a slow, gradual process playing out over cosmic eons. We're participants in something far more dynamic, more active, more rapidly evolving. The universe didn't take billions of years to set the stage for life. It was ready much sooner. And that means life could have emerged earlier, evolved longer, spread farther than we thought possible. The scale of life's potential presence in the cosmos is correspondingly larger. Maybe we're not the first intelligent species to arise. Maybe countless civilizations came before us, in earlier epochs, in galaxies that formed when the universe was young. Maybe some of them are still out there, billions of years ahead of us in development. Maybe they've explored their galaxies, left signs we could detect if we knew where to look. Or maybe intelligence is rare, despite all the opportunities. Maybe the emergence of consciousness requires such specific conditions that it happens only once per galaxy, or once per supercluster, or maybe just once in the observable universe. We don't know. But Webb's observations expand the space of possibilities. And that makes the search for life more urgent, more important, more promising than ever. The James Webb Space Telescope has revealed the true scale of the universe. And that scale is larger, more complex, more surprising than we ever imagined. Not just in distance, though the observable universe remains 93 billion light-years across, but in the amount of structure within that space, in the number of galaxies, the mass of those galaxies, the pace at which they formed, in the timeline of cosmic evolution, which is faster and more efficient than our models predicted, in the density of organization, with the cosmic web taking shape in the first billion years rather than over many billions, in the potential for life, with habitable conditions arising earlier and persisting longer. The universe we thought we understood was a simplified version of reality. A sketch based on limited data and reasonable assumptions. Webb has given us higher resolution, and that resolution reveals details that change the story. Galaxies forming when they shouldn't. Black holes growing faster than physics should allow. Structure appearing billions of years too early. Complexity emerging from simplicity at impossible speeds. These observations are forcing us to rethink our theories, to question our assumptions, to build new models that can account for what we're seeing. That process is uncomfortable because it means admitting we were wrong. But it's also exhilarating because it means there's still so much to discover. The universe isn't finished surprising us. Every time we think we've figured it out, new observations reveal deeper mysteries. And that's how it should be. Science is not about reaching final answers. It's about asking better questions. It's about refining our understanding incrementally, knowing we'll never achieve perfect knowledge, but striving for it anyway. Webb is helping us ask those better questions. It's showing us where our models fail, where our assumptions break down, where our predictions don't match reality. And in doing so, it's guiding us toward deeper truth. The true scale of the universe, as Webb reveals it, is not a fixed number. It's a moving target, expanding as our instruments improve, as our observations become more precise, as our understanding deepens. We measure scale in light years and galaxy counts, but we also measure it in complexity, in organization, in the capacity to create structure and order from chaos. By all those measures, the scale is larger than we thought, and by all those measures, we're just beginning to grasp how vast reality truly is. We stand at a remarkable moment in human history. We have the technology to see across billions of light years, to look back nearly to the beginning of time, to observe galaxies forming in the cosmic dawn. We can test our theories against observations of unprecedented precision. We can map the structure of the universe from the smallest scales to the largest, and we're discovering that the universe is more magnificent, more intricate, more awe-inspiring than we ever imagined. That's what Webb has given us. Not just data and images, though those are extraordinary, but a renewed sense of wonder at the cosmos. A recognition that we live in a universe of almost incomprehensible scale, filled with trillions of galaxies, each containing billions of stars, each star potentially hosting worlds. A universe that organized itself from simple initial conditions into staggering complexity in far less time than we thought possible. A universe that's been capable of supporting life, intelligence, and consciousness for longer than we realized. And a universe that's still full of mysteries, still hiding secrets, still waiting to reveal itself to those who have the curiosity to look and the patience to observe. The true scale of the universe is not something we can fully comprehend. Our brains didn't evolve to grasp distances of billions of light years or quantities of trillions of galaxies, but we can measure it, calculate it, represent it mathematically. We can build instruments that extend our senses beyond their natural limits, and we can stand in awe of what we discover, humbled by our smallness against the cosmic backdrop, yet proud of our ability to reach out and touch that vastness with our telescopes and our minds. Webb has shown us that the universe is bigger, not just in size, but in every dimension that matters. More complex, more organized, more capable, more full of potential. And in showing us that, it's shown us something about ourselves. We're part of this vast cosmos, evolved from the same processes that form galaxies and stars. We're made of atoms forged in stellar furnaces, scattered by supernovae, gathered by gravity into planets, organized by evolution into consciousness. We're the universe's way of knowing itself, and through Webb, we're seeing ourselves more clearly than ever before, seeing our origins in the first galaxies, seeing our context in the cosmic web, seeing our place in a universe far grander than we imagined. The true scale of the universe, as revealed by the James Webb Space Telescope, is a scale that inspires awe, demands humility, and invites exploration. It's a scale that reminds us how much we've learned and how much remains to be discovered. And it's a scale that promises the adventure of understanding will never end, because the universe will always have more to show us if we're willing to look. Let's dig deeper into what these discoveries actually mean for the numbers. Before Webb, we calculated galaxy populations using something called luminosity functions. A luminosity function describes how many galaxies exist at different brightness levels. Lots of faint galaxies, fewer bright ones, following a predictable distribution. We'd survey a patch of sky, count galaxies at different brightnesses and distances, then extrapolate to the full observable universe. Those extrapolations gave us the 200 billion to 2 trillion galaxy estimate. But the extrapolations assumed we were seeing a representative sample. If faint galaxies exist in greater numbers than our surveys detected, the total count goes up. If distant galaxies are brighter or more numerous than we thought, the count goes up. Webb is showing both of these things are true. Faint galaxies in the early universe are more numerous than Hubble could detect. Bright galaxies exist at distances where we didn't expect any galaxies at all. When you recalculate using Webb's data, the numbers change dramatically. One study estimated that the galaxy count in the observable universe might need to be revised upward by a factor of 2 to 5. That would push the total to 4 trillion to 10 trillion galaxies. Another study, focusing specifically on the first billion years after the Big Bang, found galaxy densities 10 times higher than previous models. If that ratio holds across all cosmic epochs, we're looking at even larger revisions. 10 trillion galaxies. 20 trillion. The exact number depends on assumptions about how galaxy populations evolve over time, but all the revisions point in the same direction. More galaxies than we thought. Significantly more. And each galaxy contains stars. If the average galaxy holds 100 billion stars, which is probably conservative, then 10 trillion galaxies means 10 to the 23rd power stars. 1 followed by 23 zeros. For comparison, there are about 10 to the 23rd power grains of sand on all of Earth's beaches. The number of stars in the revised universe would equal or exceed the total grains of sand on our planet. But stars aren't uniformly distributed across galaxies. Some galaxies, like dwarf galaxies, might have only a few million stars. Giant elliptical galaxies might have 10 trillion or more. The Milky Way, with its 400 billion stars, is above average but not exceptional. When you account for this distribution, the total number of stars in the observable universe could easily reach 10 to the 24th power. 10 times more stars than grains of sand on Earth. That's the scale we're talking about. And every one of those stars is a sun. A fusion reactor converting mass into energy, illuminating space around it, potentially hosting planets. We know from Kepler Space Telescope observations that planets are common. Most stars have at least one planet. Many have multiple planets. If even 10% of stars have planets in the habitable zone, the region where liquid water could exist on a planet's surface, we're looking at trillions of potentially habitable worlds. The Drake equation, which estimates the number of intelligent civilizations in the galaxy, uses factors like star formation rate, fraction of stars with planets, fraction of planets that develop life. Every factor in that equation gets multiplied by larger numbers when you increase the total star count. If the universe has twice as many galaxies, it has twice as many stars, twice as many planets, twice as many opportunities for life. The scale of potential life in the universe increases proportionally with the scale of structure. And Webb is showing that scale is larger than we calculated. But let's focus on specific numbers from Webb's discoveries to make this concrete. Glass, Z13, one of the earliest confirmed galaxies, contains approximately 1 billion stars. At 300 million years after the Big Bang, to put that in perspective, forming 1 billion stars requires about 1 billion solar masses of gas to collapse. Actually, more than that, because not all gas becomes stars. Star formation efficiency in modern galaxies is typically around 1 to 10%. That means for every 100 solar masses of gas, only 1 to 10 solar masses become stars. The rest is blown away by stellar winds, dispersed by supernova explosions, or remains as uncollapsed gas. If we apply the same efficiency to the early universe, forming 1 billion stars might require 10 billion to 100 billion solar masses of gas to be available. But gas in the early universe is spread out, not concentrated. Gravity needs to pull it together, compress it, cool it down enough for it to collapse into stars. This process takes time. Simulations suggest that even under ideal conditions, gathering and collapsing enough gas to form a billion stars should take at least 500 million to 1 billion years. Glass Z13 did it in 300 million. That's like asking a construction crew to build a skyscraper in half the time it takes to pour the foundation. The timeline doesn't allow for all the necessary steps, unless something about the early universe made the process faster. Some researchers have proposed that gas in the early universe was denser, allowing it to collapse more quickly. But density alone doesn't solve the problem. Even dense gas has pressure, and pressure resists collapse. You need the gas to cool, radiating away energy, before it can collapse efficiently. Cooling takes time, governed by the laws of thermodynamics. You can't rush it beyond certain limits. Others have suggested that the first stars were extremely massive, hundreds of times the mass of the Sunday. These massive stars would burn through their fuel in just a few million years, dying quickly and triggering more star formation with their supernova shockwaves. Multiple generations of stars could form and die in the time frame where we'd expect only one generation. This could speed up the pace of chemical enrichment and galaxy assembly. But even with rapid cycling, you still need time to gather the gas, form the stars, wait for them to die, and use their remnants to form the next generation. 300 million years is tight, even with maximally efficient processes. Then there's JWST, GSZ 14-0, with its supermassive black hole. The black hole has a mass estimated at several million solar masses. Black holes grow by accreting matter from their surroundings. As matter spirals into a black hole, it heats up and emits radiation. That radiation creates pressure that pushes against infalling matter. This is the Eddington limit, and it sets a maximum accretion rate. For a black hole of one solar mass, the Eddington limited accretion rate is about 1/10,000,000th of a solar mass per year. That means it would take 10 million years to double the black hole's mass. To grow from 10 solar masses, the mass of a stellar black hole, to 1 million solar masses, you'd need to double about 17 times. 17 doublings at 10 million years per doubling equals 170 million years. And that assumes the black hole is feeding at the maximum rate continuously, which is unlikely. JWST, GSZ 14-0, existed less than 300 million years after the Big Bang. Even if the black hole formed immediately, which it couldn't have because you need stars to form first, the timeline barely works. And this assumes we understand Eddington limited accretion perfectly, which we might not. Some astrophysicists have proposed that black holes in the early universe might have been able to accrete faster than the Eddington limit suggests. Maybe magnetic fields or exotic matter configurations allowed super-Eddington accretion. But this is speculative, invoking processes we haven't observed to explain observations that don't fit our models. Another possibility is that these supermassive black holes didn't form from stars at all. Maybe they formed directly from collapsing gas clouds in the early universe. If a sufficiently large and dense cloud collapses all at once without fragmenting into stars, it could form a black hole of thousands or tens of thousands of solar masses immediately. These are called direct collapse black holes, and they'd give supermassive black holes a head start. Instead of beginning at 10 solar masses and growing to millions, they'd start at 10,000 and only need to grow by a factor of 100 or so. That's much more achievable in 300 million years. But direct collapse requires very specific conditions. The gas cloud needs to be massive, dense, and unable to cool efficiently. If it cools too fast, It fragments into stars instead of collapsing whole. Keeping a cloud hot enough to avoid fragmentation is difficult. It requires intense radiation from nearby sources or exotic conditions we're not sure existed in the early universe. Some models invoke metal-free gas, which cools less efficiently than gas with heavy elements. The first galaxies would have metal-free gas, so this might work, but even then, the conditions need to be just right. It's not clear that direct collapse was common enough to explain all the supermassive black holes Webb is finding. The density of massive black holes in the early universe is higher than direct collapse models predict. Either the models are missing something, or we need a new mechanism for forming massive black holes. This is one of the biggest puzzles Webb has uncovered. Another specific number that challenges our models is the galaxy density at different epochs. Pre-Webb models predicted that at z equals 10, which corresponds to about 480 million years after the Big Bang, the universe should contain about 5% of the galaxy density we see today. That number comes from simulations that track how dark matter halos form and how gas falls into those halos to make stars. The simulations are based on the Lambda CDM model and match observations of the recent universe very well. But when Webb measured galaxy density at z equals 10, it found closer to 20 to 30% of today's density. 4 to 6 times more galaxies than predicted, at z equals 13. About 330 million years after the Big Bang, models predicted maybe 1% of today's density. Webb found closer to 10%, 10 times more galaxies. These discrepancies are systematic, meaning they appear consistently across different surveys and different methods of counting. It's not measurement error. It's a real mismatch between theory and observation. To reconcile these observations with theory, we'd need to change some fundamental assumption about how galaxies form. Maybe dark matter halos form faster than simulations predict. Maybe gas falls into those halos more efficiently. Maybe star formation is triggered more easily in the early universe. Any of these changes would require modifying the Lambda CDM model, adjusting parameters, or adding new physics. But modifications aren't simple. The model has many interconnected parameters. Change one, and you affect others. Adjust the rate of dark matter halo formation, and you might break the model's fit to the cosmic microwave background. Increase star formation, efficiency, and you might predict too many stars in modern galaxies. Every proposed solution creates new problems. This is why cosmologists are talking about a crisis. The observations are solid. The models don't fit. And finding a way to fix the models without breaking everything else has proven extremely difficult. The structure and organization of early galaxies add another layer of complexity. Pre-Webb models predicted that galaxies in the first billion years would be irregular, chaotic blobs of stars without much internal structure. Spiral arms, galactic disks, organized rotation, all of these features should take billions of years to develop. Spiral arms form through density waves, patterns that sweep through a rotating disk, compressing gas and triggering star formation. But density waves require a stable disk, and stable disks require time to settle. When galaxies form through mergers, the collisions stir things up, creating turbulence that prevents settled structures from forming. Only after a galaxy has gone a long time without major mergers can it settle into an organized disk with spiral arms. That's the theory. Webb is finding galaxies with disk-like structures at z equals 8 to 10, meaning 700 to 500 million years after the Big Bang. Some even show hints of spiral arm features. These structures shouldn't exist yet. the galaxies haven't had time to settle. One explanation is that these aren't true spiral arms, but just coincidental alignments of star-forming regions that happen to look organized. But spectroscopic observations show rotation patterns consistent with settled disks. The stars are moving in organized ways, orbiting a central mass, not chaotically swirling in random directions. This suggests genuine structure, not just appearance. Another possibility is that the first galaxies formed from gas that was already rotating. If the primordial gas clouds had significant angular momentum from the beginning, they might naturally form disks as they collapsed. But this requires the initial conditions to be different from what we assumed. And it's not clear where that angular momentum would come from. In the standard picture, angular momentum builds up through gravitational interactions, tidal torques from neighboring structures. This process takes time. Having significant angular momentum from the start requires rethinking how structure forms in the first place. Chemical composition provides another set of challenging numbers. When the universe began, it was 75% hydrogen and 25% helium by mass, with trace amounts of lithium. Everything heavier, carbon, oxygen, nitrogen, iron, silicon, had to be created in stars through nuclear fusion. The first stars fused hydrogen into helium, then helium into carbon and oxygen. Massive stars continued fusing, creating elements up to iron. Elements heavier than iron are created in supernova explosions through rapid neutron capture. This process, called nucleosynthesis, takes generations of stars to build up significant amounts of heavy elements. The first generation, population, 3 stars, were pure hydrogen and helium, with 0 metals. The second generation, population 2, incorporated the metals scattered by the first generation's supernovae, maybe reaching 0.1% metal content. The third generation, population 1, like our Sun, incorporated metals from multiple previous generations, reaching about 2% metal content. That's the standard timeline. It takes billions of years and many stellar generations to go from 0 metals to Sun-like metal abundances. Webb's spectroscopy of some galaxies at Z equals 8 to 10 shows metal abundances around 10 to 20% of solar. That's far higher than the 0.1% we'd expect from just 1 or 2 stellar generations. It suggests many generations of stars have already lived and died, enriching the gas repeatedly. But many generations of stars take time. Each generation needs to form, live its life, die, and scatter its metals before the next generation can incorporate them. Even if we assume population 3 stars live only a few million years, you still need time for multiple cycles. Getting to 10% solar metallicity in 500 to 700 million years requires extremely efficient cycling. Stars forming, dying, and forming again with minimal delay. This is possible if star formation is triggered rapidly and continuously, with supernova shockwaves from one generation immediately compressing gas to form the next. But it requires conditions we're not sure existed. Modern galaxies have gaps in star formation, periods where little happens. Gas needs to accumulate, cool, and become dense enough to collapse. This takes time. In the early universe, maybe those gaps were shorter because gas was denser and cooling was faster. But even with faster cycling, the timeline is tight. Some researchers have proposed that the first stars were extremely efficient at producing metals, creating more heavy elements per generation than modern stars. If population 3 stars were typically 200 to 300 solar masses, they'd produce vastly more metals when they died than a modern 10 solar mass star. This could speed up chemical enrichment. But we have no direct observations of population. 3 stars, so their properties are uncertain. We're invoking unseen objects with assumed properties to explain observations that don't fit our models. That's not inherently wrong, but it's a sign we're reaching beyond what we know for certain. The cosmic web structure, appearing early, also has specific implications for numbers. The cosmic web is the large-scale pattern of matter distribution in the universe. Filaments of galaxies and dark matter stretch across hundreds of millions of light-years, connecting dense nodes where galaxy clusters form. Between the filaments are voids, vast regions nearly empty of galaxies. This structure emerges naturally from gravity. Slightly denser regions in the early universe attract more matter, growing denser over time. As they grow, they pull matter from surrounding regions, creating filaments along the lines of strongest gravitational attraction. Simulations of structure formation show that the cosmic web takes billions of years to develop its current form. At z equals 10, about 500 million years after the Big Bang, simulations predict the web should be barely forming, with only the densest regions starting to clump. Webb's observations of protoclusters and galaxy groups at z equals 10 and beyond suggest the web was already well developed. Dozens of galaxies gravitationally bound together, organized into structures that will become today's massive clusters. These protoclusters contain tens to hundreds of galaxies in regions only a few million light-years across. The density is much higher than the universe's average density, indicating significant clumping has already occurred. For gravity to create such dense clumps in 500 million years requires matter to flow inward faster than simulations predict. This could happen if dark matter halos form more quickly, providing deeper gravitational wells. Or if dark matter is more concentrated than we thought, creating stronger gravitational attraction. Either way, something about structure formation is more efficient than our models allow. The distribution of matter also affects predictions about dark energy. Dark energy is the mysterious force causing the universe's expansion to accelerate. We don't know what it is, but we can measure its effects on cosmic expansion. One way to study dark energy is to measure how structure grows over time. If dark energy's strength changes over cosmic history, it affects how fast structure forms. Webb's observations of early structure could, in principle, constrain dark energy's history. But only if we understand how structure forms in the first place. If our models of structure formation are wrong, we can't use structure to test dark energy. This is another way Webb's discoveries complicate cosmology. They introduce uncertainties into measurements we thought were solid. We need to fix our models of galaxy formation before we can confidently use those models to probe dark energy, dark matter, or other fundamental aspects of cosmology. Let's talk about the implications for the total mass in the universe. The observable universe's mass is dominated by dark matter, which makes up about 85% of all matter. Normal matter, the stuff that makes stars and planets, and us, is only about 15%. We estimate the total mass by measuring the gravitational effects on light and galaxy motions. When light passes near a massive object, the object's gravity bends the light's path. This gravitational lensing lets us map how mass is distributed, even if we can't see the mass itself. Pre-Webb estimates suggested the observable universe contains about 10 to the 53 kilograms of total mass, including dark matter. That's a 1, followed by 53 zeros. For perspective, Earth's mass is about 6 times 10 to the 24 kilograms. The Sun's mass is about 2 times 10 to the 30 kilograms. The Milky Way's total mass, including dark matter, is about 10 to the 42 kilograms. The observable universe's mass is about 10 trillion Milky Way galaxies worth. But if there are more galaxies than we thought, and those galaxies are more massive on average, the total mass goes up. Each additional trillion galaxies adds about 10 to the 42 kilograms to the total. If Webb's observations push the galaxy count from 2 trillion to 10 trillion, that's 8 trillion additional galaxies. 8 times 10 to the 42 is close to 10 to the 54 kilograms. Adding that to the existing 10 to the 53 gives about 10 times 10 to the 53, which equals 10 to the 54. So the total mass of the observable universe might be 10 times higher than we calculated. That's an order of magnitude increase. Of course, these are rough estimates. The actual numbers depend on detailed calculations of galaxy masses, dark matter distributions, and cosmic volumes. But the principle holds. More structure means more mass. And Webb is showing more structure than we expected. This affects the universe's overall density, how much mass exists per unit volume. Density matters because it determines the universe's geometry and ultimate fate. If density is too high, the universe's gravity will eventually overcome its expansion, causing it to collapse in a big crunch. If density is too low, the universe will expand forever, eventually becoming cold and empty. There's a critical density where the universe is balanced, neither collapsing nor expanding to emptiness, but approaching a stable endpoint. Current measurements suggest the universe is very close to this critical density, possibly exactly at it. But those measurements depend on knowing how much mass exists. If we've underestimated the mass, the density is higher than we thought, and the universe's fate might be different. Actually, the current understanding is that dark energy dominates the universe's dynamics, so density alone doesn't determine fate. Dark energy is causing expansion to accelerate, which will lead to eternal expansion regardless of matter density. But the exact trajectory of that expansion depends on how much matter there is to slow it down. More matter means slower acceleration, which changes when galaxies beyond our local group will disappear beyond our horizon. It changes the timeline of cosmic evolution over trillions of years. These are long-term effects, but they matter for understanding the universe's ultimate fate. Another aspect of scale involves the energy budget of the universe. Energy and mass are related through Einstein's equation, E equals mc squared. The total mass of the universe represents an enormous amount of energy. But there's also energy in motion, kinetic energy of galaxies moving through space, thermal energy of gas and stars, radiation energy from light propagating across the cosmos. And there's dark energy, the mysterious component driving accelerated expansion. Dark energy is thought to make up about 68% of the universe's total energy content. Dark matter is about 27%. Normal matter is about 5%. These percentages are based on measurements of the cosmic microwave background and observations of large-scale structure. But if there's more normal matter than we thought, organized into more galaxies, the percentages shift. Maybe normal matter is 6 or 7% instead of 5. That doesn't sound like much, but it affects the balance of forces shaping cosmic evolution. More normal matter means more gravitational attraction, more structure formation, more complexity. It also affects predictions about nucleosynthesis, the process that created elements in the Big Bang's first minutes. Nucleosynthesis is extremely sensitive to the density of normal matter. Too much normal matter, and you produce too much helium and deuterium. too little, and you don't produce enough. The observed abundances of these elements match the predicted 5% very well. If normal matter is significantly more than 5%, we'd need to revise nucleosynthesis models. But those models are among the most successful in all of physics, matching observations to incredible precision. It's hard to imagine they're wrong. So maybe normal matter really is 5%, and the extra galaxies Webb sees don't significantly change that. Maybe the additional mass is in dark matter, which doesn't participate in nucleosynthesis. But then we need to explain why dark matter would be distributed differently than our models predict. Why it would clump into galaxy halos more efficiently in the early universe. Again, we're forced to revise our understanding to accommodate Webb's observations. There's also the question of what powered the first galaxies. Stars produce energy through nuclear fusion, converting hydrogen into helium and releasing energy in the process. But stars aren't the only energy source. Actively accreting black holes can outshine entire galaxies. As matter spirals into a black hole, friction heats it to millions of degrees, causing it to emit intense radiation across the spectrum from radio waves to X-rays. This radiation can be so intense that it blows away nearby gas, affecting star formation across the entire galaxy. Webb has found that many early galaxies contain actively accreting black holes, objects we call active galactic nuclei, or AGN. The fraction of early galaxies hosting AGN seems to be higher than in the recent universe. Maybe 20 to 30% of galaxies at Z equals 8 to 10 show signs of active black holes. In the modern universe, only about 1 to 5% of galaxies have active nuclei. This suggests black holes played a more important role in the early universe than we realized. They weren't just passive bystanders, but active participants in galaxy evolution. Black hole radiation can heat gas, preventing it from cooling and collapsing into stars. This is called feedback, and it regulates star formation. Too much feedback, and star formation shuts down entirely. Too little, and all the gas becomes stars, leaving none for future generations. The balance between star formation and feedback determines how galaxies grow over time. If early galaxies had more active black holes, they experienced more feedback, which should slow star formation. But Webb shows rapid star formation in these same galaxies. How do you reconcile intense black hole activity with high star formation rates? Maybe the feedback doesn't affect the entire galaxy uniformly. Maybe it creates a complex pattern of regions where star formation is suppressed and others where it's enhanced. Or maybe our understanding of feedback is incomplete, and black holes affect their host galaxies in ways we haven't accounted for. This is another area where Webb's observations are forcing us to rethink established ideas. The temperature of the early universe also plays a role in these calculations. As the universe expands, it cools. The cosmic microwave background, at a temperature of about 2.7 degrees above absolute zero today, represents the cooled remnant of the hot plasma that filled the universe's first few 100,000 years. But the universe wasn't uniformly cooling. When the first stars ignited, they heated the gas around them. Their ultraviolet radiation ionized hydrogen, stripping electrons from atoms and creating bubbles of hot, ionized gas expanding outward. These bubbles eventually overlapped, reionizing the entire universe by about 1 billion years after the Big Bang. This period, called the Epoch of Reionization, is one of the key transitions in cosmic history. Before reionization, the universe was neutral, filled with hydrogen atoms that absorb ultraviolet light. After reionization, it was ionized, transparent to ultraviolet. Webb's observations are helping us understand when and how reionization happened. By identifying the most distant galaxies, we can see which ones existed before reionization and which formed after. The early galaxies Webb finds are numerous enough that they could have produced the ultraviolet radiation needed to reionize the universe. But some models predicted you'd need even more galaxies, fainter ones we can't yet detect, to provide enough radiation. Webb's findings suggest the galaxies we can see might be sufficient. Their star formation rates are high enough, and there are enough of them, to do the job without invoking additional unseen populations. This simplifies our understanding of reionization, but it also means the star formation rates in these galaxies are at the high end of what's possible. Any higher, and they'd produce more ultraviolet radiation than observations allow. Any lower, and you'd need more galaxies to explain reionization. The numbers are constrained from multiple directions, and they all point to early galaxies forming stars very efficiently, very rapidly, in quantities significantly higher than pre-Webb models predicted. Beyond the observable universe, the scale becomes even more mind-bending. If the universe extends beyond what we can see, and most cosmologists think it does, then the total scale is vastly larger than 93 billion light-years. Some models, based on cosmic inflation, suggest the total universe could be at least 10 to the 23rd times larger than the observable universe. That's a number so large it defies comprehension. If you took the observable universe and copied it 10 to the 23rd times, you'd start to approach the total universe's size. And if each copy contains 10 trillion galaxies, the total number of galaxies becomes 10 to the 34. 1 followed by 34 zeros. At that point, numbers lose all meaning. You can't visualize it, can't comprehend it, can only write it down and acknowledge it exists. But here's the thing. If the universe is that large, and if it's roughly uniform, then everything that can happen will happen, not just once, but infinitely many times. Somewhere in that vast expanse, there's another galaxy identical to the Milky Way, another solar system identical to ours, another Earth with another version of you. In fact, there are infinite copies, each living out slightly different versions of history. This is sometimes called the Level 1 multiverse, the idea that if space is infinite and matter is roughly uniform, all possible configurations must occur somewhere. It's philosophically disturbing because it removes any sense of uniqueness. But it's also a logical consequence of infinite space and finite matter configurations. Webb can't directly test this idea because we can't see beyond our horizon. But by showing that the observable universe is more densely packed with structure than we thought, Webb makes the Level 1 multiverse, if it exists, correspondingly richer. More galaxies per unit volume means more complexity, more diversity, more opportunities for interesting things to happen. And if that pattern extends to infinity, the scale of reality becomes truly incomprehensible. There's also the temporal scale to consider. The universe is 13.8 billion years old, and it will continue existing for trillions upon trillions of years. Current models predict that stars will continue forming for another 100 trillion years or so, until the gas is exhausted. After that, existing stars will burn out over tens to hundreds of trillions of years. Eventually, the only objects left will be black holes, which will themselves evaporate through Hawking radiation over timescales of 10 to the 100 power years. That's a 1 followed by 100 zeros, far longer than the current age of the universe. Webb's observations don't directly affect these long-term predictions, but they do change our understanding of the universe's history. If structure formed faster and earlier than we thought, the universe has been active and complex for a larger fraction of its total age. Instead of spending the first billion years in a dark, simple state, it was already filled with galaxies, stars, and black holes after just a few 100 million years. That's less than 3% of the current age. By comparison, if the universe were 1 year old, 300 million years would be about 8 days. The universe went from darkness to galaxies in the first week of its year-long existence. And those galaxies weren't primitive. They were sophisticated, massive, organized. The universe hit the ground running, so to speak, organizing itself with remarkable speed and efficiency. This changes our sense of cosmic history. We thought the early universe was a period of slow development, gradual emergence of complexity. Webb is showing it was a period of explosive growth, rapid transformation from simple to complex. That shift in perspective matters when thinking about the universe's timeline as a whole. If rapid change can happen, if the universe can transform itself dramatically in a few 100 million years, what else might change on short timescales? Will there be future epochs of rapid transformation, or was the early universe special in some way? These questions don't have answers yet, but they're important for understanding cosmic evolution as a whole. The psychological impact of Webb's discoveries also deserves consideration. For decades, we thought we understood the universe's scale and history. We built detailed models, tested them against observations, and refined them until they matched. That process gave us confidence. We thought we were approaching a final understanding, filling in the last details. Webb has shattered that confidence. It's shown that our models were wrong in fundamental ways. Not slightly off, but missing entire aspects of how the universe works. For scientists who've spent their careers working within the Lambda CDM framework, this is jarring. Some have embraced the challenge, excited by the prospect of discovering new physics. Others are more cautious, worried that discarding a successful model might be premature. This tension is normal in science when paradigm shifts occur. Thomas Kuhn, in his book, The Structure of Scientific Revolutions, described how science progresses through periods of normal research punctuated by revolutionary upheavals. Normal research refines existing models, solving puzzles within the established framework. But eventually, anomalies accumulate that the framework can't explain. This leads to crisis, where competing models are proposed and tested. Eventually, a new framework emerges that explains both the old observations and the new anomalies. That new framework becomes the basis for the next period of normal research. Webb's observations are pushing cosmology toward a paradigm shift. The old framework, Lambda CDM, still works for many things, but fails to explain early galaxy formation. New frameworks are being proposed, tested, and refined. In a decade, we'll likely have a new standard model of cosmology that incorporates Webb's discoveries. That model will make new predictions, which future telescopes will test, possibly triggering another cycle of discovery and revision. This is how science works. It's messy, uncertain, constantly evolving, but it's also the most reliable way we have of understanding reality. And right now, reality is telling us that the universe is bigger, more complex, more rapidly evolving than we thought. The true scale, as revealed by Webb, is a scale that demands we revise our assumptions, question our models, and embrace uncertainty as we work toward deeper understanding. When we step back and look at Webb's contributions as a whole, several themes emerge. First, the universe is more capable than we predicted. More capable of forming structure quickly, more capable of organizing complexity, more capable of creating massive objects in short times. This capability suggests that the physical processes governing cosmic evolution are more efficient than our models allow. Gravity, star formation, black hole growth, chemical enrichment, all of these work faster in the early universe than we thought possible. Second, the scale of structure is larger at every level we examine. More galaxies, more stars, more massive objects, more organization, more early development. The numbers we calculated based on pre-Webb observations were underestimates, sometimes by significant factors. Third, our theories are provisional. Even our most successful models, tested against decades of observations, can be wrong in fundamental ways. This should make us humble about what we think we know and eager to test our ideas against new data. Fourth, the universe is knowable. Despite its vastness, despite the limitations of our senses and instruments, we can observe, measure, and understand cosmic phenomena. Webb is proof of that. It's showing us galaxies forming 13 billion years ago, black holes growing in the early universe, structure emerging from chaos. We can see these things, measure them, study them, and learn from them. Finally, exploration is ongoing. We're not approaching the end of discovery. We're in the middle of it, perhaps even near the beginning. Every answer leads to new questions. Every observation reveals new mysteries. The universe is an inexhaustible source of wonder, and our capacity to explore it is limited only by our imagination and ingenuity. Webb represents the current frontier of that exploration. It's our best tool for seeing the early universe, for testing theories against observation, for pushing the boundaries of knowledge. And what it's showing is that the true scale of the universe is bigger, stranger, more magnificent than we ever imagined. Not just in distance or time, but in complexity, organization, capability, and potential. That's the legacy of Webb's discoveries. Not a final answer, but an opening to deeper questions. Not an endpoint, but a beginning. The universe has revealed a bit more of itself, and in doing so, it's shown us how much more there is to learn. So where does this leave us as we try to comprehend the true scale of what exists? We started with a model that seemed solid, tested against observations, refined over decades. The observable universe, 93 billion light-years across, 200 billion to 2 trillion galaxies. A timeline where galaxies formed gradually over billions of years. Structure emerging slowly from simple initial conditions. Then Webb looked deeper than Hubble ever could, and everything changed. Galaxies appearing hundreds of millions of years earlier than expected. Densities 3 to 10 times higher in the early universe. Massive structures that shouldn't exist yet. Black holes growing impossibly fast. Organization and complexity emerging in time frames that violate our understanding of physics. These aren't minor discrepancies. They're fundamental challenges to our cosmological framework, and they force us to recalculate everything we thought we knew about cosmic scale. The number of galaxies might be 5 to 10 trillion instead of 2 trillion. The total mass might be an order of magnitude higher. The timeline of structure formation might be compressed by factors of 2 to 5. The universe's capability to self-organize might be far greater than our models predict. Each of these revisions cascades through our understanding, affecting calculations about dark matter, dark energy, the ultimate fate of the cosmos, and the potential for life beyond Earth. The scale we're measuring isn't just physical dimensions. It's the scale of our ignorance, the gap between what we thought we knew and what we're discovering. And Webb is showing that gap is larger than we realized. But that's not a failure of science. It's science working exactly as it should. We build models based on available data. We test those models against new observations. When the observations don't match, we revise the models. This process is how we improve our understanding, how we inch closer to truth. Webb is providing the observations that force revision. And while that's uncomfortable, while it means admitting we were wrong, it's also the most exciting possible outcome, because it means there's still so much to discover. The universe isn't a closed book we've nearly finished reading. It's an open frontier, vast and largely unexplored, full of surprises waiting to be uncovered. Let's think about what Webb's discoveries mean for humanity's long-term perspective. We've known for over a century that Earth isn't the center of anything. We orbit an ordinary star in an ordinary galaxy, in an ordinary region of space. There's nothing special about our location, our star, or our galaxy. This is sometimes called the Copernican principle, and it's been repeatedly confirmed by observations. But there's a corollary that's equally important. If our location isn't special, if we're a typical example of what the universe produces, then the fact that we exist suggests similar things exist elsewhere. Intelligence might not be common, but in a universe with trillions of galaxies, even rare events happen countless times. If intelligent life has a 1 in a billion chance of arising in any given galaxy, that's still trillions of civilizations across the observable universe. Webb's discoveries expand this calculation. More galaxies means more opportunities. Earlier structure formation means longer timelines for evolution. Higher densities of habitable planets in the early universe means more real estate for life to explore. The scale of potential life in the cosmos increases with every upward revision of galaxy counts. Yet we see no evidence of other civilizations. No signals, no megastructures, no signs that intelligence has spread across the galaxy or beyond. This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Webb doesn't directly address this paradox, but it makes it more acute. If the universe is even more capable of producing habitable worlds than we thought, if it's been doing so for even longer, then where are all the aliens? Maybe intelligence is vanishingly rare, occurring only once per trillion galaxies. Maybe technological civilizations inevitably destroy themselves before reaching interstellar capabilities. Maybe there's a great filter, some challenge that prevents life from advancing beyond a certain point, and we haven't reached it yet. Or maybe we're the first. Maybe, despite the universe's vastness and age, we're the earliest civilization to reach the point of asking these questions. It seems unlikely, but in a universe with trillions of galaxies, someone has to be first. Why not us? These questions don't have answers yet, but Webb's discoveries reframe them. The scale of the cosmic stage is larger, the timeline is longer, the opportunities are more abundant. And yet, the stage appears empty, or at least we haven't found anyone else on it. That emptiness takes on deeper meaning when you realize just how vast the stage truly is. There's also something profound about living in an age when we can observe these things. The universe is expanding, and that expansion is accelerating. In trillions of years, distant galaxies will have receded so far that their light can never reach us. Future civilizations, if they arise, will look at the sky and see only their local galaxy group. They'll have no evidence that the broader universe exists. No cosmic microwave background to discover, because it will have redshifted into undetectable wavelengths. No distant galaxies to observe, because they'll all be beyond the horizon. Those future beings will be cosmologically isolated, unable to learn about the Big Bang or cosmic expansion or the true scale of reality. They'll invent cosmologies based on what they can see, and those cosmologies will be wrong, but they'll have no way to know it. We're lucky. We exist at a time when the universe is still young enough, still compact enough, that we can see almost to the beginning. We can observe the cosmic microwave background, map the distribution of galaxies across billions of light years, see structure forming in the early universe. We can know the full scope of cosmic history, from the Big Bang to today, and make informed guesses about the future. That window won't stay open forever. In 100 billion years, it will have closed. We're living in the brief window when the universe reveals itself most fully, and Webb is maximizing what we can learn during that window. It's seeing the farthest galaxies we'll ever be able to see, observing the earliest epochs we'll ever be able to observe, testing our theories at the extreme limits where they're most likely to break. We should appreciate this moment. We have tools powerful enough to see across cosmic distances. We have theories sophisticated enough to interpret what we see. We have a civilization stable enough to support long-term scientific projects like Webb. All of these things could have been different. We could have evolved on a planet with a thick atmosphere that blocks astronomical observation. We could have developed in a time when the universe was too young or too old to reveal its secrets. We could have destroyed ourselves before reaching this level of technological capability, but we didn't. We're here, now, with eyes on the cosmos, seeing farther and more clearly than ever before. And what we're seeing is magnificent. Webb's discoveries also remind us of the power of collaboration. The telescope wasn't built by one person or one nation. It was an international effort involving thousands of engineers, scientists, technicians, and administrators across decades. NASA led the project, but the European Space Agency and the Canadian Space Agency were major partners, contributing instruments and launch capabilities. Astronomers from around the world competed for observing time, proposing projects that would maximize the telescope's scientific return. Once the data is collected, it's made publicly available, allowing anyone with the skills to analyze it. This open access approach has led to discoveries from researchers who weren't even part of the original observing teams. Someone in India, analyzing Webb data, might find something someone in the United States missed. A student in Europe might develop a new analysis technique that reveals hidden patterns. Science works best when it's collaborative, when knowledge is shared freely, when the global community works together toward common goals. Webb embodies that ideal, and its discoveries belong to everyone, not just the astronomers who operate it or the nations that funded it, but to all of humanity. Because understanding the universe's true scale, understanding our cosmic origins, understanding our place in reality, these are questions that transcend national borders or cultural differences. They're human questions, fundamental to our species' drive to explore and understand. Webb is giving us answers, and those answers are showing a universe richer and more complex than we imagined. That enrichment belongs to all of us. There's a certain poetry to the fact that we're made of stardust. The atoms in your body were forged in stellar cores, billions of years ago. Carbon, oxygen, nitrogen, phosphorus, all the elements essential for life, were created when massive stars died and scattered their enriched material across space. That material drifted through the cosmos, eventually accumulating into the cloud that formed our solar system. Earth coalesced from that cloud, and over billions of years, those atoms organized themselves into increasingly complex structures. Molecules, cells, organisms, eventually conscious beings capable of wondering where they came from. We are, quite literally, the universe's way of knowing itself. Collections of atoms that organized into patterns capable of thought, capable of asking questions, capable of building telescopes to observe the processes that created them. Webb is the latest expression of that capability. It's humanity looking back at our cosmic origins, seeing the galaxies that formed when the universe was young, studying the processes that created the elements we're made of, mapping the structures that eventually led to stars like our Sun and planets like Earth. We're observing the history that produced us, and in doing so, we're connecting to the universe in the deepest possible way. Not as external observers, but as participants, products of the same physical processes we're studying. The scale of the universe, as Webb reveals it, is also our scale, because we're part of it, embedded in it, shaped by it. We exist at human scales, confined to a small planet orbiting an ordinary star, but we're connected to the largest scales through our origins. Every atom in your body has a cosmic history stretching back billions of years. You are a temporary pattern in the cosmic flow, a brief eddy in the universe's ongoing transformation from simple to complex. And that pattern, that brief existence, has given rise to consciousness capable of comprehending its own cosmic context. That's remarkable. That's worth celebrating. We're small, yes. Tiny against the vastness of space and time. But we're also the part that's awake, the part that can see and understand and appreciate that vastness. We're the universe's attempt to know itself, and we're succeeding. Webb is proof of that success. As we look to the future, Webb's discoveries will shape research for decades. Thousands of scientific papers will be written analyzing its data. New theories will be proposed to explain what it's found. Those theories will make predictions, which future telescopes will test. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will complement Webb with wider field observations. While Webb stares at small patches of sky in exquisite detail, Roman will survey larger areas, finding rare objects and mapping structure across vast cosmic volumes. The extremely large telescope, once operational, will provide even sharper views of individual galaxies, resolving details Webb can only glimpse. Together, these instruments will build a more complete picture of cosmic evolution, but they'll almost certainly find new anomalies, new observations that don't fit theories, new mysteries to solve. That's the nature of frontier science. Each answer spawns new questions. Each resolution of one mystery reveals another waiting to be explored. Webb has opened a new chapter in our understanding of the universe's scale. But it's not the final chapter. It's one step in an ongoing journey that might never end. And that's beautiful, because it means there will always be frontiers to explore, always new wonders to discover, always deeper understanding to pursue. The universe is vast, and we've barely begun to explore it. Webb has shown us that the true scale is even larger than we thought. More galaxies, forming earlier, evolving faster, organized sooner. A cosmos that refuses to fit our neat theoretical boxes, that surprises us every time we look deeper. That's the universe Webb reveals. And that's the universe we're privileged to live in, to study, to wonder at, and to slowly, incrementally, come to understand. In the end, the true scale of the universe isn't just about numbers. It's not about counting galaxies, or measuring distances, or calculating masses. Those numbers are important. They're the language we use to describe what we observe. But the scale is also about possibility. The possibility that life exists beyond Earth, scattered across trillions of galaxies. The possibility that the universe is even larger beyond our horizon than we can currently imagine. The possibility that we're missing fundamental aspects of how reality works, and future observations will reveal physics we haven't discovered yet. The possibility that consciousness, this remarkable ability to contemplate existence, might be more common in the cosmos than we think, or rarer than we fear. Webb's discoveries expand those possibilities. They show a universe that's more capable, more complex, more rapidly evolving than our models predicted. And in doing so, they invite us to think bigger, to question more, to remain humble about what we think we know. The true scale of the universe, as revealed by the James Webb Space Telescope, is a scale that challenges us. It challenges our theories, forcing us to revise models we thought were solid. It challenges our intuitions, presenting us with numbers too large to comprehend. It challenges our assumptions, showing us that the universe doesn't care about our predictions. But it also inspires us. It inspires wonder at the sheer magnitude of existence. It inspires curiosity about what else remains to be discovered. It inspires hope that in this vast cosmos we might not be alone. And it inspires humility, reminding us that for all we've learned, we're still at the beginning of understanding. The universe is bigger, stranger, more magnificent than we imagined, and we're part of it. Small, yes. Brief, certainly, but capable of seeing, measuring, understanding, and appreciating that magnificence. That's what makes us matter. Not our size or our strength, or our location in space, but our curiosity, our creativity, our relentless drive to explore, to question, to seek understanding, even when understanding seems impossible. The James Webb Space Telescope embodies that drive. It's humanity at our best, working together across borders and disciplines, pushing the limits of technology, asking fundamental questions about existence. And it's giving us answers that expand our sense of scale, that deepen our appreciation for the cosmos, that invite us to keep exploring, keep questioning, keep reaching for deeper understanding. The true scale of the universe is vast, beyond imagining. But it's knowable, piece by piece, observation by observation. We're mapping it, measuring it, coming to understand it. We may never grasp it fully. The human mind has limits, and the cosmos exceeds those limits. But we can approach understanding asymptotically, getting closer with each generation, each new instrument, each new discovery. Webb is our latest step in that approach, and it's shown us that we have farther to go than we thought. The scale is larger, the complexity deeper, the mysteries more profound. But that's not discouraging, it's exhilarating. Because it means the adventure continues. The journey toward understanding the universe's true scale is ongoing, and we're living in one of the most exciting moments of that journey. We're seeing things no human has ever seen before. We're learning things no one has ever known. We're expanding the boundaries of knowledge in real time. And through Webb, we're connecting to the cosmos in the deepest possible way. Seeing the galaxies that formed when the universe was young, observing the processes that created the elements we're made of, mapping the structures that eventually led to our existence, understanding the scale of the stage on which the human drama plays out. That stage is vast beyond comprehension. 93 billion light-years across, maybe infinitely larger beyond our horizon, filled with trillions of galaxies, each containing billions of stars, organized into structures that span hundreds of millions of light-years, evolving over billions of years from simplicity to staggering complexity. That's the universe James Webb has revealed, a universe that was already immense in our previous understanding, but has grown even larger in Webb's observations. Not just in physical size, though the galaxy counts are higher and the masses are greater, but in its capability to surprise us, to challenge our theories, to reveal new layers of complexity every time we look deeper. The true scale of the universe is the scale of wonder, the scale of questions yet to be answered, the scale of exploration that will occupy humanity for as long as we exist, and the scale of our own significance, not despite our smallness, but because of it, because we're the part of the universe that's asking these questions. We're the part that's building telescopes, analyzing data, seeking understanding. We're the universe's way of knowing itself. And what we're learning, through Webb and through every observation that follows, is that the universe is magnificent, vaster than we thought, more complex than we predicted, more beautiful than we imagined, and more full of mystery than we can ever fully resolve. That's the true scale James Webb has revealed. Not a final answer, but an invitation. An invitation to keep looking, keep wondering, keep seeking to understand the cosmos that gave rise to us. And in accepting that invitation, in continuing the exploration, we honor the universe's grandeur and affirm our place within it. Small, but conscious. Brief, but capable of touching eternity through observation and understanding. Part of something vast and magnificent, connected to the stars through our very atoms. And privileged to live in an age when we can see the true scale of it all.